So now let's take a look at a simple problem here. So we go to example 3.2 from our textbook. In this problem here, they ask us to determine the natural frequency for a simple spring mass system shown in the figure below by measuring our static deflection. So now what we can see here is we have this spring with nothing attached to it here with a value, spring constant of K, and we know the length when there's nothing attached, and the unstretched length is L naught. We add this weight W to the end of the spring here, and we can see the length of the spring goes from this L naught, and it has a static deflection here denoted by use of ST. So what we can also do now is we can take and draw a free body diagram of our weight here, where we have the weight acting down on our block here, and we have our spring force acting back up. Our equation for our spring force is given to us by a K, which is our spring constant, times use of ST, our static deflection. So now that we've had a chance to go through our problem statement, the next step is to create our setup page. So on our setup page, clearly label what problem we're dealing with here, example 3.2 from lecture 3.2 in our textbook for the course ME270. This is a single degree of freedom spring mass system. We have our given diagram here. Here's our unstretched length, no mass attached of our spring right here. Spring constant K, unstretched length is L naught. We can see now we've added this weight here, stretch the spring by our static deflection denoted by use of ST here. So what do they give us? I want to clearly write out everything they've given us in the problem in one area. So my givens, I have my F sub S, my spring force is equal to K times the static deflection. My static deflection is denoted by use of ST. My L naught is the unstretched length of the spring. My K is my spring constant. And we have W as my weight. And over here now I have my free body diagram ready to go. I have my spring force up here and my weight force acting down there. Now what are they asking us to find? They want us to solve for the natural frequency of the simple spring mass system, our omega sub n. We now have our setup page completed. We can reference back to that for any of the given information or what we're looking to solve for in the problem as we're going through our solution. But in order to start our solution, we need to come up with a governing equation to relate to our natural frequency, our omega sub n. So where this governing equation comes from is equation 3.4a on page 56 of our textbook. So this right here tells us that our natural frequency squared, omega sub n squared, is equal to K over m, our spring constant divided by our mass. So this is going to be useful information to relate back for our omega sub n. So we'll keep that there when we reference back to it. The next thing that we want to do is do out that free body diagram. So they gave us the free body diagram in the problem statement, which really simplified our solution. We need to come up with that on our own. We can quickly look, okay, here's my weight. Got my weight force acting down. I have my spring force acting up. I'm going to choose a coordinate system. Now, I can see that we're only dealing with the y-axis here, but I have a force going up and a weight going down. So it's up to me. What do I want to consider my positive y? I'm going to go with my standard Cartesian. One's going to be negative, one's going to be positive, so it really doesn't make one way more complicated than the other. So I'm just going to stick with my standard y positive up, x positive to the right. Come over here and say, okay, summation of forces in the y direction is equal to 0. The thing's static. So therefore, we say, okay, what are my forces acting in my y direction? Well, I have my W, my weight force acting in my negative y direction, negative W. And I have my spring force acting in my positive y direction, F sub S. And this is equal to 0. So rearrange this. Our weight is equal to our F of S. So from that equilibrium mass equation we just had, we have this relationship here, our summation of forces in the y direction, that weight is equal to our spring force. So with that relationship there, we also know we have a value for our spring force given to K times its distance it stretches, so our spring constant times the distance it stretches, which is our static deflection times the K value they give us in the problem statement. So now we have this relationship for F of S that we can plug back up in here to the equation we got from our forces in the y direction. We do that there and we see that weight is equal to K times our static deflection here, use of ST. So plug in, we know that weight is equal to mass times the acceleration due to gravity. We can plug that in there. What we end up with is that mg is equal to K times our static deflection here of use of ST. We can solve this for m. We now get a relationship for m. The m is equal to our spring constant K times our static deflection all over the acceleration due to gravity. So with all that information, we now have enough to go back to our governing equation, which again was from 3.4a in our textbook, where omega sub n squared is equal to k over m. We know now we have this relationship for m, so we can plug this relationship here in for our m there. Plug this in, we can see that now we have omega n squared is equal to k over, now we have this whole value here for m, spring constant k times our static deflection here over acceleration due to gravity. Flip this around, put the g up top there. Omega sub n squared is equal to k g over k times static deflection here. You can see our k's cancel out. When our k's cancel out there, we now have omega sub n squared is equal to g, acceleration due to gravity over our static deflection there. Take the square root of both sides. Omega sub n is equal to the square root of g over our static deflection.